Okay, Algebra 2, here we go into section 3.3, and if I were in charge of the world, I probably would have flip-flopped 3.2 and 3.3. I probably would have done this section right after we got done with 3.1, where we were solving systems of equations by graphing. So let's look at the title right here of what we're going to be doing in 3.3. We are graphing and we are solving systems of linear inequalities. So the only real difference between this and 3.1 we were doing linear equations, solving by graphing, and now we're doing inequalities. So this is going to take us back to just a little bit of what we did towards the end of chapter 2, in section 2.8, when we were graphing linear inequalities one at a time. Now we're going to be doing a system, which means there are going to be multiple inequalities. But the concept hasn't changed at all. We shade the points that work, and we don't shade the points that don't work. And, much like we've been talking about with systems lately, we're looking for solutions now, and solutions are going to be points that satisfy all of the statements given to us in a system. So let's start off with number 1, which is about the easiest example I could come up with right here. We've got two one-variable inequalities. X is greater than -2, which I'm going to graph in blue, and then we'll come back in red, and we'll graph the inequality y is less than 3. So what I'm hoping you guys remember is that these are some of the weird statements right here that only have one variable. And when you have a statement like your first one here, x is greater than -2, with no y, that, if it's just x, is when we have a vertical line. And this number right here, which we've called a in the past, -2 in this case, is your x-intercept. So on the x-axis, we're going to go to -2, and we're going to put a dot there. And technically, I think it should be an open dot, because at that point, x is -2. -2 is greater than -2 is a false statement. It's not true. And so for that reason, I wouldn't shade that dot in. But not many Algebra 2 teachers care that much about that. Now, we're going to draw the one and only vertical line that has that x-intercept. But because this symbol here is just greater than and not greater than or equal to, this is going to be a dashed line. That's why I put the open dot there as well. And I'll put the arrows on both ends of that. And now, we have to worry about shading. We want to shade all points out there that satisfy this statement right here, where I'm erasing right now. All the x values greater than -2. Well, as you recall, your x-axis, of course, runs horizontally. It goes to the right and it goes to the left. The lesser values on the x-axis are out here on the left. The greater values are out here on the right. And since we want to know all points that have an x value greater than -2, greater means we shade to the right. So I would shade the entire right half of this graph here. Every point that's in that shaded region now satisfies this statement. Every point on the right there has an x-coordinate greater than -2. Okay, that wasn't too bad. Now let's take a look at graphing the second one simultaneously. Y is less than 3. And since this inequality has only a y and not an x, this one, hopefully we remember, is a horizontal line. And this number here, in this case it's 3, we call that b in general. That is your y-intercept. So since my y-axis runs vertically, I'm going to go up 3 units, and I'll place an open dot there. Again, you don't want to close it in technically, because 3, which is the y-coordinate at that point, is less than 3. Nope, that also is a false statement, and that's why I wouldn't shade that dot in. Doesn't really matter too much, but this does matter. The horizontal line that we draw through that point is going to be dotted as well, because again, the symbol is just less than, not less than or equal to. So we'll put a dashed or a dotted line going through there, and I'll put arrows on the end, and we have to shade here as well. Now this one goes back to the way we normally did things at the end of chapter 2. A less than sign always means that we shade below. So everywhere below that red line, I'm now going to shade like this. Every point in this red shaded region has a y-coordinate that's less than 3. Now, this is where things get a little bit tricky here and maybe a little bit different when we're solving a system of linear inequalities as opposed to a system of linear equations. If you remember back in 3.1, we would come up with a graph of, okay, here's one line and then here's the second line, and you are interested in this point right here where they intersect, and I would make you guys write out the solution. Maybe that's the point -2, -1, sure, and you box it up, and that's your answer. It's your only answer because with equations, there was only one ordered pair that satisfied both of those original two statements. But let's ignore that now. Things are different for us now when we're dealing with inequalities. Now, what we're looking for are the set of all points that satisfy both of the original two statements. So let me switch over to green right here. We're looking for ordered pairs that satisfy this statement, an x value greater than -2, and this statement, a y value less than 3. So if we look at the graph here, guys, we're interested in points that satisfy both. So what we're looking for, a phrase you're going to hear me use a lot, is the double shaded region. And the double shaded region is the part of the coordinate plane that is shaded both by the blue shading and also by the red shading. And what you see here, guys, and I think you got it, this entire region here in kind of the lower right-hand part of this graph is your solution. Every single point here that's to the right of the blue line and below the red line is a solution. Now there's three other regions. These points up here, they satisfy the first statement, but not the second. That's why they're shaded just in blue. These points over here satisfy the second statement, but not the first. That's why they're only shaded in red. And these points up here, they don't work for either of the two statements. So in terms of how do you actually answer a problem like this, really the graph is your answer. When we got it to this point, that's really where we stop. Now, there are an infinite number of points that are in this double shaded region, but what I'm going to have you do, guys, is just write down for me one example solution. Now, I want to be clear, this is not the only solution, this is just one point. And if I were to choose, I don't know, I'm just going to randomly pick this point right over here, that looks like it's in the double shaded region. That ordered pair we came up with right there is, let me see, starting from my origin right here, I guess I could have used the origin, 1, 2, 3, 4 units to the right, and then it looks like it's 2 units down. So the ordered pair 4, -2 is in the double shaded region. That should be an example of one point that satisfies both of the original two statements. Let's check it. At that point, our x value needs to be greater than -2. Well, our x value here is 4. So 4 is greater than -2. Is that a true or a false statement? That one's true, so check, it works there. And in the second statement, our y coordinate, which is -2, has to be less than 3. Is that a true statement? Yes, it is. So that's a check as well. So this ordered pair, 4, -2, is certainly not the only solution, but it's an example of an ordered pair that works, that satisfies both of the original two statements. But again, guys, for these problems, your graph is really your answer to the question here. You can't just list the answer because there's not just one answer. There's an infinite number of points that work. Okay, so that was a relatively easy example because we were just dealing with horizontal and vertical lines and they were very quick and easy to graph. Let's take a look at a second example here. And now we're kind of easing into it right here. I did give you one equation that was in slope-intercept form, and then another one that is, again, a special case. So let's deal with the first one here, guys. Y is less than or equal to 2x minus 4, and that's in slope-intercept form. So our y-intercept, let me make this graph just a little bit bigger. We have the room for it here. Our y-intercept, then, is -4. And so, all right, I'm going to go down 4 units and make a dot. And now in this case, our inequality symbol is less than or equal to. That's when we go ahead and shade the dot in because of the or equals to on the bottom. So a y-intercept of -4 and a slope of +2. Up 2, right 1, up 2, right 1, up 2, right 1. When we were solving a system of equations, it was really important that we were super precise, and I would have made you guys write out as many points as you can here. That's less important when we're doing a system of inequalities where we're just going to be shading. Okay, next thing to consider is that a solid or a dashed line, because of the or equals to, that's going to be a solid line here passing through all of those collinear points, arrows on both ends, and now we have to shade. If you can help it, don't think about left or right. Think about above or below. And when y is less than or equal to 2x minus 4, we shade below the line, which is going to be everything here in this region. So there's an infinite number of points in that shaded region that satisfy this first statement. Now the second statement, y is greater than or equal to 3. Well, like we just talked about in the last problem, there's no x, so this is a horizontal line, and 3 is your y-intercept. So right up here, and I'm putting a solid dot because it's greater than or equal to. And for that same reason, this is going to be a solid line and not a dashed line coming across. So there in red is the line y equals 3. And now we need to shade either above or below. So we look at the inequality sign, y is greater than or equal to 3, and with greater than, that means that we shade above. So I've graphed the blue line, and I've shaded part of that of the graph. Then I graphed the red line, shaded part of it as well. And again, our answer then, everybody, is the double shaded region, which looks like it's up here. So just to show you guys what it is that we're accomplishing right here, let me come up with one more example solution, an ordered pair that's in that spot. And if I chose the point, I don't know, how about this one right over here? That appears to be in the double shaded region. Let's see if it works. Counting backwards, it looks like that ordered pair is 7, and then I think 5 for my y coordinate. Let's see if it works. In the first statement, y, which is 5, is less than or equal to 2 times, right here guys, 2 times our x value of 7, which is 14, minus 4. Okay, I'll clean up that right side. 5 is less than or equal to 14 minus 4 is 10. And ask yourself, is that statement true or false? Is 5 less than or equal to 10? Yes, it is. That's a true statement, and that's what I was expecting. The second statement will be much easier to test. My y-coordinate at this point is 5. So 5 is greater than or equal to 3. Well, that statement right there is clearly true, and this one works out as well. Now, just for fun, let's think about the origin for a second, just because it's an easy point to work with. The ordered pair 0, 0 appears to be in the region that wasn't shaded at all. Now that tells us something, guys. The ordered pair 0, 0 should not satisfy the blue statement, nor should it satisfy the red statement either. We should end up with 2 falses when we test that one out. So real quick, there's really no point in writing this down, but here we go. Let's test it right here. Our y-coordinate is 0. Is less than or equal to 2 times 0 is 0. 0 minus 4 is negative 4. So let's look at that statement. 0 is less than or equal to negative 4? No, it's not. That's a false statement, which I expected because this green dot at the origin was not in the blue shaded region. Nor should it work in the red. Let's check it. For the second inequality, our y-coordinate at the origin is 0. 0 is greater than or equal to 3? Nope, that's a false statement as well. So that doesn't surprise me because this origin point is not in the red shaded region either. Now, just for fun, if I were to pick a point down here somewhere, think about it, that one should work in the original statement right here. It should satisfy the first statement because it's in the blue region, but it should not work in the second statement because it's not in the red shaded region. And likewise, if I were to pick a point up here somewhere, that point is in the red but not the blue. That should not satisfy the first statement but it should satisfy the second. We won't walk through all of that, but that's just kind of the way to interpret what your graph actually looks like. But as I said earlier, the answer to your problem here is really the graph that you've come up with. So I'll take this back to this spot right here and then say, okay, that's good enough. But this region up here, that's what we're looking for in that top right section. Okay, the plot thickens a little bit here, everybody. We're going to start seeing some inequalities here that are written in standard form, that are not given to you in slope-intercept right off the bat. Okay, and I bring this up because there's that one little tricky thing about solving inequalities that sometimes rears its ugly head, and I think we could probably use a reminder of that. But before we go any further here, guys, let's dive into it. In the first inequality right here, we want to solve this for y. So we're going to subtract a 9x from each side. And that's going to leave us with 3y is greater than, and I think we'd prefer that as negative 9x minus 12. Then we're going to divide every term by 3. And when we're dividing in an inequality by a positive number, nothing weird happens. This is pretty straightforward. We're going to end up with y is greater than, let's see, negative 9 divided by 3 is negative 3x, and then negative 12 divided by 3 is minus 4. So here is my first inequality now solved for y. I could graph this now, but I think for a reason you'll see in a second, I'm going to hold off here. And I'm going to solve the second inequality now for y, and then we'll graph them both simultaneously. Okay, trying to get y by itself, we're going to subtract a 6x from each side, and that is going to leave us with a negative 8y is greater than or equal to a negative 6x minus 16. And now to get y by itself, we're going to divide each term in this inequality by negative 8. Now those negatives cancel, and we end up with y. And now, everybody, here's the thing I'm hoping you remember from the end of chapter 2. When you are multiplying or dividing, and in this case we're dividing, both sides of an inequality by a negative number, which in this case is negative 8, that is when you have to flip your inequality sign right here. It was greater than or equal to, but now that we've divided by a negative, it flips into less than or equal to. Now let's keep going. Negative 6 over negative 8, well, a negative over a negative is a positive, and 6 over 8 simplifies into 3/4. So that's a positive 3/4 x. And then negative 16 divided by negative 8 is a plus 2. And there is the second statement. Now the second inequality, and this one is solved for y as well. So now, let me see what I can do here, guys. I wanted to move this over and maybe make this graph a little bit bigger. Let's run with that. Yeah, we've got a pretty good view at what it is that we're looking at here, guys. All right, we're going to graph each of these two at the same time. And I realized I did something weird in this problem that is going to show up in your homework a little bit too. You'll see what I mean in just a second. All right, first inequality here. Y is greater than negative 3x minus 4. Y-intercept of negative 4. And I put an open dot, and I'm not going to fill it because the inequality sign is just greater than, not greater than or equal to. Our slope is negative 3, so we would go down 3, right 1, which would get us right about here, but I'm kind of out of room, so now I'm going to go the opposite direction. Up 3, left 1. Up 3, left 1. Up 3, left 1. Those open dots aren't super important. If you fill them in, that would be fine, but what is important is that we are putting a dotted line here, again, because the inequality sign is just greater than, not greater than or equal to. So there's our line, and now, of course, with every inequality, we have to shade. And because this is y is greater than, I'm looking at this symbol right here, greater than always means that we shade above our line. And so there we go. We've shaded half the coordinate plane. Those are all the points that satisfy this statement right over here. Now let's move on to the second one here. In red, y is less than or equal to 3/4 x plus 2. Our y-intercept is 2, so I put a dot there, and now I'd think, should that be an open or a closed dot? Well, because this inequality symbol is less than or equal to, the or equal to means that the border points work here, and we fill them in. Our slope is 3/4, so up 3, right 4. Kind of ran out of room to do that again, so now I'm going to go down 3, and left 4. Down 3 and left 4 if you have the room. And there you go. We've got 4 collinear points there. Okay, solid or dashed line. Again, because this symbol is less than or equal to, the or equal to means that we're going to do a solid line passing through all of those points there. Okay. Boy, that doesn't look very straight to me. Did I do that right? Down 2, 3. Yeah, I think I did. Okay, gotcha. And now we have to worry about shading. The symbol here is less than or equal to. And with less than, we always shade below the graph. So I'm looking at this spot right over here. The weird thing about this problem, I commented on this just a second ago, one of your lines is solid and one of your lines is dashed. That's kind of unusual, but it certainly can happen, so just be aware that that's the case. Now, if we were actually solving a system of equations, this would be kind of a pain right now because the point of intersection between these two lines is right there. Ugh. And that kind of looks like it has in fact, I'm sure it has non-integer coordinates. So there'd be fractions involved right here. But lucky for us, we're not trying to write one particular ordered pair. We're really not that interested in our point of intersection. Remember, our answer here is the graph. We're looking for the double shaded region, which is kind of this area right over here. And of course, remember, it goes on forever out here to the right and then kind of down there in that spot as well. And if I were looking for a solution, well, okay, I should get back to what I told you guys a while ago. The origin is the easiest point to think about, 0, 0. That point is in the double shaded region. So the origin should work here, guys. It should satisfy both of the original two statements. And to test that, speaking of what I just said there, I'm going to go back to the originals. Now, I'm not a big fan of standard form. I think I've told you guys this, but one great thing about standard form, using the origin is really, really easy because the left side of your equation or inequality in standard form always becomes 0. Let's think about that. 9 times 0 is 0, 3 times 0 is 0, and 0 plus 0 is 0. So testing the origin here, in the first inequality, we get 0 is greater than negative 12. True or false? That one's true. So I feel pretty good so far. Now let's test it on the right. 6 times 0 is 0. 8 times 0 is 0, and 0 minus 0 is 0 again. We get 0 is greater than or equal to negative 16. That one is true as well. So I chose a point, the origin, a really easy one to work with, that was in my double shaded region, and that point, when I went back and checked, did satisfy both of the original two statements, so I feel really confident about my answer right now. All right, guys, I got 2 more examples to do with you, and I think I remember what I was going for in this one right here. So let's take a look. Just like the last problem that we did, this one has 2 statements, written in standard form. So we've got a little work to do to solve for y. Here, we're going to subtract a 4x from each side here. Those cancel. We'll get a negative 6y is greater than, and a negative 4x plus 18. Then we're going to divide every single term, there's 3 in most cases, by negative 6. So we're going to get y. Let's see if we've learned it here, guys. We just divided both sides of an inequality by a negative. So we flip, and I always like to make a big stink about the fact that I'm doing that there. We flip the greater than sign into a negative. Negative 4 divided by negative 6 just simplifies to positive 2/3 x, and then that'll be a minus 3 at the end. So there is the original statement, there is the first inequality, but this one is now solved for y, and we'll graph that in a moment. Let's take a look at the second one now. Negative 6x plus 9y is greater than negative 9. Getting y by itself, we're going to add a 6x hither and thither. All right, those cancel. We're going to get 9y is greater than, and that'll be a 6x minus 9. We will divide each of the 3 terms here by 9, but here we're dividing by a positive number. So there's no need to flip the sign. And we're going to get y is greater than 6 over 9 simplifies to 2/3 times x, and then a minus 1 at the end of all that. And as we're just about to get started graphing this, I want you guys to take a look at these two lines that we've come up with here in the blue box and in the red box, and you might notice something interesting is about to happen. And if you didn't, well, you'll probably notice when we graph it. Here you go. First line, everybody. Y is less than 2/3 x minus 3. Down 3 units for our y-intercept, and it's an open dot because it's just less than. Our slope is 2/3. So up 2, right 3. Up 2, right 3. Up to, okay, I get it. There you go. This one's going to be a dashed or dotted line passing through those open dots. Okay, so it looks like that. And since this inequality symbol is less than, we're going to shade everywhere below that line there. Okay, pretty easy so far. Now the second one. Something interesting happens here. Our y-intercept for this red line is -1. So I'll put an open dot right there, open because the symbol is just greater than, not greater than or equal to. And our slope, which you probably noticed a minute ago, is the same here as it was for the blue line. Up 2, right 3. Up 2, right 3. Up 2, right 3. And now we will draw again a dotted line that passes through all of those red dots here. Okay, it looks like that and it looks like that. And now where are we shading? This inequality symbol is greater than. And with greater than, that means that we shade above the line that we just drew. So, in every problem that we've done so far, let's go back and look at them real quick here, guys. In every problem that we have done so far, our answer has been the double shaded region, and I've kind of marked it up in green there in most of these graphs. We're looking for points that satisfy both of the original two statements, so that's what we call the double shaded region. So looking for the same thing right here, where do we have a double shaded region? Where do we have points that satisfy both the original blue statement and the original green statement at the same time? And the answer to that, first time it's shown up in this section right here, we have no solution to this system of inequalities. There is no ordered pair, not one, that is in both the blue shaded region and also in the red shaded region. It is impossible for a value right here to work on both of those at the same time. So this is the first one of these examples that we've seen here when you never have a double shaded region, when you never have any overlap between your two shadings. That's when we would say that our answer to this problem is no solution. So yeah, that one hasn't happened yet, but it certainly can. Okay, and the last example, I wanted to give you one just to scare you a little bit here, guys. And yeah, right away you can see what's going on here. We are looking here, everybody, at a 3 inequality system. All right, we've got 3 statements right here, and each one of them is going to need to get graphed at the same time on the same coordinate plane. Now, I tell you what, I'm going to make this bigger and easier to see. The nice thing about this problem is all 3 of those are already solved for y, so we don't have to do any work to prep for this one. We can just dive right in. So here we go. Statement number 1, let me do this one in blue. Y is greater than 2x minus 4. I feel like I gave you that line already today. Y-intercept of -4, so it's right here with an open dot and a slope of 2. Up 2, right 1, up 2, right 1. Okay, we get it. All right, that one is going to be a dotted line because it's just greater than, and because it's greater than, we are going to shade above. Now, I'm going to try to be really careful not to make my shading too messy right here, but we are shading above the blue line, so it's kind of top and left. All right. Let me switch to red right here for inequality number 2. Y is greater than or equal to -3x minus 4. So we go 4 units down, and we'll put a dot there, same y-intercept, but this dot is going to get shaded in red because it's greater than or equal to. And our slope is -3. Down 3, right 1 would be right about there, but of course I could also go up 3, left 1, up 3, left 1, up 3, left 1, and I think that's pretty good. This one is going to be a solid line because it's greater than or equal to. All righty, gotcha. And with greater than, we shade above. So This is what our graph looks like so far, and up until this point I've been telling you guys to look for the double shaded region, the region that satisfies both of the original two statements. Well, that kind of looks like this region right here. But the plot thickens here, guys. When you have a three inequality system, now, I'll go green with this one, now we're looking for points that satisfy not just one, all three of the original inequalities. So I also need to graph the third one here. Y is less than 1/5 x plus 1. We'll go up 1 unit and make an open dot there, and then our slope of 1/5 is up 1 and then 5 to the right. Up 1, 5 to the right. And of course we could have gone down 1 and then 1, 2, 3, 4, 5 to the left, down 1, 5. Okay, good enough. This one is going to be a dashed line yet again. Okay, looking like that. Then means that we are going to shade below this green line here. So I'm shading carefully here everything we can below the green line. So now we've graphed 3 lines and we've shaded 3 regions. So now our solution is not the double shaded region anymore, it is the triple shaded region. And it's tough to see, but it looks like we have a triangular region right here in the middle, guys, that looks like it is shaded by both the blue and the black. The blue and the red and the green. And I think that this little triangular region here in the middle is going to be our triple shaded region, that all 3 inequalities are going to be satisfied. Now, probably not surprising, I think I did you a favor right here. I think the origin is in that triple shaded region. So the point 0, 0 should work in all 3 of these statements. Let's test it. In the first statement here, y is 0. That should be greater than. 2 times 0 is 0, minus 4 is negative 4. Is 0 greater than negative 4? Check. Yes, it is. How about statement 2? Y is 0. That should be greater than or equal to. Negative 3 times 0 is 0, minus 4 is negative 4. That's the exact same statement again. Check, it still works. 0 is greater than or equal to negative 4. And into the third statement, y is still 0. That should be less than 1/5 times 0, that's 0, plus 1 is 1. So is 0 less than 1? Yes, it is. So we picked a point in the triple shaded region, and that point satisfied all 3 of the original statements. So now I feel pretty confident about my answer. All right, guys, that's everything I've got for you here in section 3.3. Hopefully that all sank in. I don't think it's too tough of a section. So let's give that homework a try, and good luck, everybody.